So today what we're going to do is we're going to take the moles idea and we're going to get it together with the stoichiometry BCA table idea and kind of arrive at the point where most people are doing stoichiometry, like people who do chemistry on a routine basis are going to do it in this particular fashion. So I've given you some flaps on your way in, and what I want you to do is cover up this BCA table, because what I'm going to show you today is that there are actually two possibilities on your BCA table. Now, as you put down today's flaps, you have to be kind of cognizant of the flaps from the time before, not to get things stuck down, because you're going to end up here with a 3-layer paper showing you 3 different possibilities for how you can do this. But today what I want to show you is that when we're working with BCA tables, we have a rule that says no grams allowed in the BCA table, no AMUs allowed in the BCA table. We've been putting particles in the BCA table, but that has happened with some pretty uncomfortable numbers, like things to the 23rd, things times 10 to the 22nd, 23rd, 24th. Lots of really big numbers that are kind of hard to think about. The other possibility for building a BCA table that kind of cleans things up a little bit is to run moles through your BCA table instead of running particles through the BCA table. And what you're going to find is that in the case of limiting reactant problems in particular, it's a lot easier to have it end up that way, because it's a lot easier to look at it and kind of know right away which one is going to be my limiting reactant. So the goal here today is to take stoichiometry, solve it using moles instead of number of particles, and prove to you that at the very end, we can land at exactly the same answer. So we have our BCA table flap in, and then your 2 other flaps, again, you have one small and one large. We're going to use the small one first to cover up here, okay? But again, kind of be cognizant that you can get to all the other layers underneath here. And I'm even going to cover up the red, figure out how many particles part. So we're going to redo this operation, operating in moles instead of operating in particles, and make sure that we can land at exactly the same place. So remember, the context here was the baking soda lab when I gave you a certain desired amount that you wanted to have after the decomposition was done. And I picked for myself a mass that I wanted. I said that I was going to use, or that I wanted to end up with 2.85 grams of the sodium carbonate. So if we redo this in terms of moles, instead of asking myself how many particles I want in the beaker when all is said and done, what I really want to know is how many moles of Na2CO3 is equal to 2.85 grams. And now if I peek under the flap, I have an information statement that says 6.022 times 10 to the 23rd sodium carbonate particles is equal to 105.988 grams. We're just going to tack one more piece onto the end of this information statement. So we're going to pull the information from the flap below, 6.022 times 10 to the 23rd particles is equal to 105.988 grams. And we've learned that the third piece of that statement is that we call that 1 mole of Na2CO3. So we just brought 2 ideas from the bottom and added our newest idea. I'm starting in grams. I'd like to go to moles, which means that in this operation, we're going to get rid of the yucky numbers altogether. We're not going to use this 6.022 times 10 to the 23rd particles. We're going to go straight grams to moles. Bring down the only number from your problem, 2.85 grams. One mole of sodium carbonate is equal to 105.988 grams. .85 divide by 105.988, 0.0269 moles Na2CO3. And I'm just going to put a little note under here, needed at the end. So I don't lose track of what question I'm really trying to answer. Because remember, the goal here was to have that much left at the very end. So now instead of putting number of particles into my BCA table, I'm going to grab this number and I'm going to pull this number into my BCA table. When this reaction is done, I'm going to need to have 0.0269 moles. And then I'm going to fill in my BCA table, but I'm going to use this less yucky number to fill in my BCA table. So to get from 0 to where we want to be at the end, I have to gain 0.0269 moles. It is going to require 2 sodium bicarbonates for every 1 sodium carbonate that I want to make. So that means I'm going to have to spend 2 sodium bicarbonates for every 1 sodium carbonate, and I plan to have in the end 0.0269 moles. So 0.0269 times 2. So it's going to cost me 0.0538 moles in order to make 0.0269 moles. And what's starting to happen here is by having moles in the BCA table instead of particles, it's much easier to see the 2-to-1 ratio that's showing up in the change row. When we had all those really complicated numbers, it was a little harder to look at these ratios and say, are we good? But this is a lot easier. I can look at this number and I can see that the sodium bicarbonate is roughly double of the sodium carbonate that I want in the end. And so that's good. And if this is the amount I want to spend and I want to land at 0, I must need to start with 0.0538 moles up here. And we don't really need the rest of the BCA table. We could fill it in if we wanted to, but you're going to kind of get to the point, I think, where you only fill in the parts that you actually need. So what we know now is that instead of stating how many particles we're going to start with, we're going to make the statement that we are going to start with 0.0538 moles of sodium bicarbonate. So that makes our BCA table look a little better. We aren't chasing around after these giant numbers anymore. They're easier to put into our calculator, less margin for error. I think we're going to be better off operating in moles. So then the last flap is going to have to go here. And we got to be a little bit careful not to pin down the BCA table. So now we just got to go back the other way. Since you had to load your beaker full of baking soda using a balance, we've got to figure out how many grams of the sodium bicarbonate, NaHCO3, is going to be equal to 0.0538 moles. I already have some of the information I need. If I peek below my flap, here's my 6.022 times 10 to the 23rd sodium bicarbonate particles is 84.006 grams. So pull that much forward. Equal to 84.006 grams is equal to 1 mole of NaHCO3. I'm going to go from moles back to grams. Start with the only number in your problem. One mole of this stuff weighs 84.006 grams. The moles cancel. 0.0538 times 84.006. 4.52 grams of sodium bicarbonate needed to run this reaction. And look at that. We have exactly the same answer that we had when we did this before. So what you now have compiled into one place is all of the different ways you can do stoichiometry, as well as kind of the evolution of our process here. Because we began this class with the drawing of particles on pieces of paper, we started our process in particles because that's the part that made sense to us. We just had to think about upscaling our picture. And because we had talked in the first semester about the mass of those particles in AMUs, at the point that we just had a handful of them drawn on a piece of paper, it initially kind of made sense to get you guys to think about them in terms of the mass of an individual particle in AMUs, and then just give you the conversion factor. Then we shortcutted the process a little bit with our discovery of Avogadro's number, that if we wanted to use the numbers off the periodic table in grams, we just had to start thinking in increments of Avogadro's number of particles. That would make, instead of the unit being AMU, the unit be grams, and we could get to particles a little bit more quickly. And then, in our last class, we decided that maybe, kind of like we think about eggs in dozen, it might be handy to package up our particles into little groups. And we decided that it would make sense to pack them into Avogadro's number worth. And so the other possibility is that when we need to know about the number of particles we have, that we do it packaged, or in terms of little bundles. And so today we did things in terms of moles. looking back at our BCA table, because BCA tables replaced pictures, BCA tables had to have particles in them. That's why we made the sign that says no grams or AMUs allowed in the very exclusive BCA table clubhouse. So we kept converting to number of particles for our BCA table because that's what the BCA table was doing for us. It was replacing the picture with all the different particles on it. But then we found a different way to count particles. Moles is really a count of how many particles, just like dozen is a count of how many eggs. It's just a different way to count the particles. And since moles is just another way to count particles, it was fair to put moles in the BCA table. So today, we put the moles into the BCA table, but that meant that at the very end, when we had to come back to grams again, we were coming from moles, and so we had to use the mole concept, but we landed at exactly the same place. The reason I've had you build this tri-layer document is to show you that any one of these methods will land you at exactly the same spot. By the end of today, you will have tried all of them, because I'm going to have you do a lab today, and I'm going to kind of force you down the path of trying to think in terms of moles, so kind of using the yellow layer as your model. In the end, it does not matter which of the three methods you decide you like best, because we've managed to prove that all three methods yield exactly the same answer. After you've had a chance to try all the different ways, and we've tried the bottom flap and we've tried the second flap, and today we're going to try the toppest of the flaps. After you've tried them all, you can pick the one that makes the most sense to you and the one that you feel the most comfortable working with. Okay, so we have basically come to the point of what I call eikenstoichiometry like a big chemist. This is how it's going to get done from this point forward. This is how it's going to get done when you go to college, and that's why your homework tonight says eikenstoichiometry like a big chemist.